Now let's talk chemistry. We're doing nuclear chemistry. Last concept we're going to cover here. We're getting down there. Nuclear chemistry is defined as a study of reactions that take place at an atomic level. So what's taking place at the atom level? All right, now, in order to do that, we have to have two different understandings of how things work. We have what emissions, which are particles that are products, and a bombardment, the particle is a reactant. So if we start with a particle, we call that a bombardment. If we end with a particle, we call that an emission. Now, what particles are we talking about? Well, there are a total of 6 total different emissions. 5 of them are actually particles. When we first started doing this, the scientists were beginning to name things in Latin in biology, and the chemists, not wanting to be outdone, said, hey, if they're doing Latin, let's do Greek. So the first 3 particles they identified were alpha, beta, and gamma. Eventually they decided that was silly, so they just changed it and just named them for what they were. But an alpha particle, and if you go to some old chemistry textbooks, you'll see that symbol there, that's Greek letter alpha, is 2 protons and 2 neutrons. Now, if you remember, we talked about atomic mass, atomic number, 2 protons, 2 neutrons, atomic number 2, it's the nuclei of helium. So whenever you have a helium gas, that's actually an alpha emission that you're retracting. The second particle is beta. What's left is electrons. So since there is no element that is an electron, we put an E for electron, 0 and -1 because it's negatively charged. We then talked about gamma. Gamma is down here. Pure energy, that's when the binding energy would hold that nuclear, falls apart, comes apart. The energy that's released, that's gamma energy. Since there's no particles, we leave those 2 squiggly lines. Then after that, we just started naming them for what they were. So a proton is a proton. Remember, proton nuclei would be hydrogen, atomic number, atomic mass, both 1. A neutron or a neutrino is a neutron, so therefore there's no particle there, and 1/0. And the last one there is a positron, particle of the same mass electron but having the opposite charge. So it looks the same as the beta emission, but instead of being negative, it's positive. So those are the particles that we have. Now, a little quick history. There are 3 scientists that, 4 scientists actually, 3 groups of scientists. Becquerel and the Curies, Marie and Pierre, working in France, did a lot of work with radiation. They all died of cancer, unfortunately, because they didn't know what they were dealing with. They just put uranium and radium and all this kind of stuff in their pockets, and it killed them. But the really significant thing about this is that Marie Curie, she was a PhD in chemistry. So, I mean, that's pretty cool. And in Germany at the same time, there's a scientist named Rankine. Rankine worked with X-rays. So these were the beginning of the historical understanding of atomic theory. And another thing we need to look at is how we measure radiation. There are a lot of different things. There are grays, there are REBs, relative biological effects. But the most common one are rads. Sounds like something a skater dude would say, yeah, it's rad. No, rads are units of radiation expressed in that way. All right, now, additional terms, a couple of things. We did talk about isotopes before. We need to bring them back. Same number of protons, but different number of neutrons. Many isotopes are radioactive, and that's why we talk about it at this point. Radiation, the particles that are released from a substance at an atomic level. So those, alpha, beta, neutron, proton, positron, all of those are considered radiation. Radioactive is the material that releases in radiation. And decay, a concept we're looking at now, is a process of release of radiation or breakdown at an atomic level. So those 4 concepts, make sure you have them down in your notes. Pause the video if you need more time. All right, good. Last thing we're looking at then is called transmutation, expressing nuclear change in a reaction form. Now, remember, we're talking atomic mass and atomic number to be equal on both sides of the reaction. So we take the atomic mass, the number of protons and neutrons, atomic number, the number of protons, and make sure they're the same on both sides. All right, so let's take a look at one. Here we have a carbon molecule, carbon 6, carbon 14 actually, because it's a radioactive isotope here. We use this in carbon dating. Now, what is carbon dating? Carbon dating is 2 carbons going out for a good time on a Friday night? No. Carbon dating is a way of determining the age. Now, I am going to talk a little bit about this, okay? Evolution, all that kind of stuff, I don't buy into it. I'm sorry, it doesn't make sense. Entropy, second law of thermodynamics, says we go from order to disorder. So, no. But carbon dating, this is something that evolutionists will point to. So we're saying that carbon dating is, the age of the Earth is really old. Not so much. About 10,000 years, really accurate. Beyond that, it's a bit of a crapshoot. So that's where it's at. That's where I'm at with it. All right, so let's take a look here. If I have 6 and I have 7, what number would we add to 7 to get 6? -1. What number would I add to 14 to get 14? That would be 0. So look at my particles. I'm going to grab, wrong one. Grab the one above it. There we go. That goes up there. That's the particle that we're going to use. So that would be a beta emission, because it's a beta particle and it's on the product side. Emissions are products, bombardments are on the reactants. All right, let's take a look at this here then. So if we take this one, 36, 35, that is 1, 81, 80, that's 1. So that would be, grab the wrong one again. Here we go, this one, H1O1, and that's going to be a proton emission. So the next one, we're looking at 8 going to 7. So this one is going to be -1 over 0. And it's on the reactant side. So this is going to be, since it's a beta bombardment. All right. Did I spell that wrong? Yes, I did. Let's fix that. All right. Third one over here. We're going to take 53, 53. So that's going to be 4 over 0. There is no 4 over 0, but we can take 4 over 1 and then put a 4 in front of it. So we're going to have 4 proton emissions. Okay, and the last one over here, if we take a look at 92, 82, that's 10. 207, 20, that's 20. So we don't have a 20 over 10, but we do have a 4 over 2, and we can put a 5 in front of that. So we say it's 5 alpha emissions. So again, if it's on the reactant side, it's a bombardment. On the product side, it's an emission. We have to know those particles, alpha, beta, proton, neutron, positron. So as far as particles, gamma, we don't worry about too much because it's just energy. All right. Now we do have one last thing that we can talk about. So we'll talk about transmutational series. This actually happens often in reactors material, where we go from one thing to another and keep going down until we get to the end process. So look at this one here, 92. 14 times 0 is 0. That's going to be 92. And then 238, 14, that's 224. So therefore, this would be a neutron emission. A neutron particle on the product side, that's why it's an emission. Now, when we do the series, what we get for that first product will be the reactant in the next reaction. So we'll slide it over and look at the next one, 92. 92 minus 1 would be 93. 93, we're going up, we're going to change the element. Atomic number changes, the element changes. And then 224, 0 is 224. So we're going to get neptunium. Neptunium's right next to uranium on the periodic chart. Neptune 224 over 93. Now we're going to take that and slide that. Oh, and what are you going to call that? That's going to be a beta emission. Again, it's on the product side. That's a beta particle. Slide that down for the next one. All right, 5 times 1 is 5. 93 minus 5 is 88. 224 minus 5 is 219. 88, periodic chart. Look it up. We get radon, 219 over 88. And that's going to be this particle right here. Look at those 5. That is a proton, and it's on the product side. So it's a proton emission. During the series, we're going to slide it back down again. All right, now 3 times 2, that's 6. 6 from 2 is 82. 3 times 4 is 12. 12 from 219 is 207. Periodic chart, Atomic number 82, looking at the chart. Atomic number to find the element. Lead, 207 over 82, and that particle there is an alpha product side, alpha emission. Now, this is common. Lead is often the material that we use to bring to a completion of a transmutational series, and that's why lead is often used to reflect radiation, because it's the end of the series. When we use lead, we use them in X-ray protection, put them over your reproductive organs so that you're not exposed to radiation, which would cause mutations in your offspring. We don't want that. So that's the process that takes place in transmutational series. All right, let's take a look at a couple practices. Pause the video. See if you can fill in the elements here. I'm giving you both the particles, so you just have to identify the element, use a periodic chart, make sure atomic number, atomic mass is the same. Pause it, give it a shot. All right, here we go, the answers. So first one we have thallium 273 over 69, and that's an alpha bombardment because it's on the reactant side. The second one, it is a neutron emission because it's on the product side. All right, very good. Any questions? Let me know. We're done. Take care. God bless. Bye.